listening to Life, the Universe, and Everything Else. Today on the show, the extraordinary science of everyday things. Life, the Universe, and Everything Else explores the intersection of science and society. Original music is produced by Ian James, and this episode was edited by Marissa McCool. Find her on Patreon at patreon.com/QAF. My name is Ashlyn Noble, and I'll be your host tonight. With me today, I have Jem Newman.
Hello.
Laura Creek Newman.
Hi there.
And Lauren Bailey.
Hello.
I wanted to repurpose a cool segment that I wrote for a newsletter. That's what they used to call segments back when they were written down. Newsletter segments. So I wrote for my medieval group's newsletter a piece of how glass comes to be colored, because one of the most frequent questions that I get when I'm demonstrating my glass working is, do you paint them? Or how do you get the color in the glass? Stuff like that. People have no idea. And until I started making stuff out of glass, I had no idea either, because I had no reason to go look up that kind of information. It's amazing how much stuff around us is like that just is, and we don't question it.
Mm-hmm.
The chemistry of colored glass. One of the best things about glass is its huge array of beautiful colors. As a glass artist, I get asked a lot, how do they put the colors in the glass? Or do you paint them when they cool down? The truth is, I buy all of my bead-making glass in handy rods, and I have nothing to do with how it gets colored. But I love how my knowledge of glass has grown through researching the answers to questions that people have asked me that I haven't been able to answer. The majority of glass that we use today is of a formula called soda-lime glass, and the glass that was manufactured pre-1880s was usually either soda-lime, which is sodium carbonate, calcium carbonate, and silica, or, and I do not remember which is the correct way to pronounce this, potash? Potash?
Yep.
Is it potash?
Potash.
It's a horrible word, I don't like it. Which is potassium carbonate, calcium carbonate, and silica. Pure silica can be made into glass, but its melting point is around 3,600 degrees Fahrenheit, which is ridiculous.
Oh, wow.
I didn't realize that.
Yeah, so not even able to melt it in the kind of kiln that I had.
On Earth.
Right.
Literally need to throw it into the sun.
I'm sure a volcano would do, I'm sure.
Right.
If it works for a magic ring, it'll work for glass.
Yeah, now we know what the One Ring was made of.
So the funny thing is, when you add sodium carbonate, soda, to the pure silica glass, it reduces the melting point significantly to about 1,800 degrees Fahrenheit. But it has a problem. Does anyone happen to know what this problem is? Any guesses?
No.
I had no idea. It makes the glass soluble in water.
What?
Right?
That's
not
wild.
the most useful.
Oh my god, I want to see that happen. That sounds so cool.
Imagine if you had a glass of water and it just started dissolving. Oh no.
Amazing. Oh, is that what candy glass is made of?
I don't know.
No, I know.
No, it's
I
not.
know.
So the final addition of calcium oxide, lime, stabilizes the glass. The end result is about 70% silica. In both cases, the natural unchanged glass color is typically a transparent blue or green, but it can be anything from a deep amber to the palest blue, depending on the composition of the sand that was used as the source of the silica. The biggest contributor to natural glass color without adding anything is traces of iron. Iron! So, of course, because humans are terrible, this has meant that deposits of sand low in iron have been valuable throughout glass-making history, including today, and people have fought wars over them, and etc.
Okay.
Because that's a rational thing to kill people over.
Right? Low
Humans
iron
will-
sand.
Yeah, humans will find any reason to kill each other.
So an even less understood component of glass color was the chemistry of the heat source used to melt the glass, particularly the availability of oxygen. Less oxygen tends to result in bluer glasses, as bluer iron oxides are produced by the reducing environment, whereas an excess of oxygen often results in the greener oxides. So this can even happen over the course of a day of glassmaking, as oxygen levels gradually change inside the furnace. And this was really not understood.
Oh, interesting.
Unnaturally colored glass can be produced in 4 main ways, all of which essentially involve adding metal to the batch of molten glass. But the way that they interact chemically and physically determines the color of the finished glass. Number 1, adding transition metal oxides or rare earth metal oxides. The metal ions in the glass absorb particular wavelengths of light, giving the glass its color. This was the first purposeful coloring method learned by early glassmakers. Different concentrations and purities of minerals and oxides used impacted the exact color that was produced. So that was the easiest one. You throw something in, makes it a different color. Very good. The formation of what are called colloidal particles is number 2. These are particles that are suspended throughout the glass, most often through the addition of gold or selenium, followed by heating and cooling it in a particular way. This is how most light-fast reds and pinks are achieved, so that's why those are very expensive colors of glass.
I was going to make a Head and Shoulders joke when you said selenium, but I can't think of any, so...
This is also an interesting way that you can make really cool effects on your glass. It's called like streaking or stuff like that. And fuming. Very cool. The Venetians figured out in the 15th century that adding low concentrations of things they were already using, like manganese and selenium, in small amounts to remove the color imparted by iron gave them a much clearer glass. So that's the third way, is just sort of decolorizing naturally colored glass. Decolorizing the glass allowed for more variety and brilliance of other colors. The fourth way is the addition of already colored particles, like tin oxide, which creates an opaque milk glass, which was invented right around 1575, which is the end of the period that we study. So there's the 4 ways that you can color glass. Most of the stuff that I work with is number 1, a little bit of number 2, the transition metal oxides and colloidal particles.
Neat.
Cool.
So
cool.
some examples of which elements and metals make which color, which is what I always want to know. To make white, you can use tin, arsenic, or antimony. To make purple, you can use manganese or nickel. To make blue, you can make cobalt, of course, and copper, lots of different cool copper things. Green, iron, chromium, and copper. Yellow is achieved with cadmium sulfide and lead. Amber is achieved with carbon and sulfur. Red is made with pure copper, gold, or selenium oxide, and black is often carbon or nickel. It is possible to mix additives to achieve new colors. Many new glass colors are still introduced each year, although the spike in energy costs is having a huge impact on fuel-hungry glass manufacturers. Combinations like cobalt and chromium will produce a blue-green glass, for example. So next time you see a strand of lampwork beads, even at Michael's, you can think about how much work went into figuring out how to make them all those different colors.
Cool.
Very cool.
That's great.
Do not breathe in these various metals.
No.
Yeah, it's a bad
No.
idea.
Yes, metals generally shouldn't go in you. Not in your nose, anyway.
All right, Jem, you're up next. You were covering a topic that we have. It's incredible that we have not covered this topic in depth, and I hear that you're going to go in depth.
Yeah.
Strap in, folks.
Yeah, so try to contain your amazement. This is going to be a long segment. So this has been on my to-do list for probably a decade now. I am going to talk about the hidden science of the everyday phenomenon that we know as the placebo effect. So I'm going to start off with the assumption that people might not know what a placebo is.
Every me and every you.
So the word placebo, which is Latin for pleasing or acceptable, literally meaning I please, has been used in medicine since at least 1785, though its definition has changed quite a bit over the last 3 centuries. In the 18th century, the term placebo apparently denoted a remedy that was in common use, while in the 19th century it came to mean a medicine that was prescribed more to placate the patient than to provide any real medical benefit. So if you've ever been to a doctor and been told that you had a cold, but insisted on getting a prescription for antibiotics anyway, that would be in keeping with this earlier definition of placebo, since antibiotics aren't effective against viral illnesses. But it's the modern definition that concerns us today. So in modern usage, a placebo is any medical intervention, be it a drug or a procedure, that is designed to be of no therapeutic value. So this raises the question, of course, why do we need placebos? Listeners have probably encountered the term placebo most often in the context of a placebo-controlled trial. Control is the operative term here, so in this case, the placebo is used to minimize the number of differences between the intervention group and the control group in a clinical trial, a scientific study. The intervention group, they get a pill that they have to take twice a day, for example. Then the control group does too. It just doesn't have any of the active ingredient in it. The intervention group gets an IV. Well then, so does the control group, only it's saline instead of, vancomycin or whatever. Not that you would ever consider doing a placebo-controlled trial of
Somebody
antibiotics.
called the ethics board on Gem.
Well,
Did they ever
I guess
color-
you wouldn't consider doing that here. 1950s Alabama, on the other hand.
Hey, Stan, you're an Alabama.
Jem, do they color the saline to make it different colors?
That's a good question. I don't know.
If
I think
the
they would be more
medication
likely
is-
to make the bag itself opaque because
Yeah, that makes sense.
I'm not sure what they would use to color it. It'd have to be something that is safe going directly into a vein. It's not being processed by the stomach or anything. So I'm not sure, but
That it's not cadmium and copper like glass.
yeah. Yeah, so I'm not sure off the top of my head, but it wouldn't surprise me if they there are definitely ways for them to disguise the color.
Right.
Now, of course, it's probably poor form to be glib about the Tunguski syphilis experiments, and it's not as if the Canadian government wasn't funding horribly unethical nutritional research on indigenous populations around the same time, so as I'll get into a little bit later, medical ethics has improved a skosh in the intervening years. But to get us back on track, using a placebo control, rather than just using a no intervention group, has some benefits. It allows you to maximize the similarities between the way the experimental groups are treated, helping to guard against bias. It makes it a lot easier to maintain blinding for both the subjects and the investigators themselves. Every subject is handed a pack of pills or what have you, and ideally, no one knows whether they've received an active ingredient or an active intervention or the placebo. In December 1955,
Great Scott!
Dr. Henry Beecher published an influential paper in the Journal of the American Medical Association. In it, he described the placebo as a clinical tool, quote, to distinguish pharmacological effects from the effects of suggestion and to obtain an unbiased assessment of the result of experiment. So it's important to distinguish conceptually a placebo from just any old experimental control. So a study may be placebo-controlled if it's investigating a condition that isn't particularly serious or a condition for which no effective therapy is available. But basic research ethics will generally forbid the use of a control that is unlikely to be effective in treating a serious condition or a condition that we already know how to treat. Hence, my vancomycin experiment being unlikely to be approved by the ethics board. Generally, a placebo is meant to be clinically inert. So, in a trial of acupuncture for pain management, for example, you might use sham acupuncture as a control, where instead of inserting needles, you might simply press a toothpick against the subject's skin. In that case, it would be reasonable to describe the toothpick as a placebo. However, if your trial is interested in distinguishing whether it matters where you place the needles, i.e. whether you place them in the correct acupuncture points or not, the patient who has their needles inserted at random is not receiving a placebo, as they're still getting poked. It is a control, but it's not a placebo control. Incidentally, such trials have been done and concluded that inserting acupuncture needles at random is just as effective as inserting them into the prescribed acupuncture points, which is to say, somewhat effective, but not hugely so.
But how could that be? There's so much BS around the points.
And yeah, it depends what you're what you want it to be effective for. It's a little bit effective for pain, maybe, but probably not for nausea, and not effective, for example, for fertility, which one of our associate profs at U of M uses it for. Oh well. But what if you're using needles, but you just lightly poke the skin without a full insertion? Is that a placebo? As you can imagine, it can be a bit tricky to determine whether a placebo is truly inert or not. Trickier still, once you begin to consider the so-called placebo effect. So what is that? I think most people have probably heard of the placebo effect. But I think that few, outside perhaps those involved directly in medical research, could confidently say specifically what the placebo effect is, what it refers to. The phrase has a mysterious, perhaps even magical quality to it, and raises important questions about what we mean when we say that a medicine made us feel better. The placebo effect, or the placebo response, is both easy to define and complex to explore. So let's start with an example. Let's say a cancer patient presents to their doctor complaining of nausea resulting from their new chemotherapy drug. The doc says, "I've got just the thing," and gives them a packet of sugar pills. The patient takes them, and at the next follow-up appointment, miracle of miracles, they report that their nausea is much improved. That is the placebo effect. Well, kind of. Technically speaking, the placebo effect is whatever measurable difference occurs in a patient or group of patients receiving a placebo compared to patients who receive no intervention at all. But in our example, and indeed in most clinical trials, we don't actually have a no intervention group. So we can't say for certain how much of the effect that we observed can be attributed to the placebo and how much of it is down to the natural history of the disease or to other factors. Let's move on to a different question, though. We'll get back to this one. How strong is the placebo effect? Well, it depends, but let's get this out of the way right off the bat. It is not very strong. Now, it's worth considering that many active medications also have small effect sizes. One of the reasons clinical trials are needed to tease out whether an intervention actually works in the first place, and if so, how much. For example, statins, such as Lipitor, are a mainstay of care in patients with high cardiovascular risk. But when you run the numbers, as Taylor et al. Did for the Cochrane collaboration in 2013, you discover that you would have to treat 56 patients for 5 years in order to prevent a single heart attack, and 96 patients for 5 years to prevent a single death. It's actually a little bit more complicated than this, of course. That assumes that we're talking about primary prevention, not secondary prevention, and depends on underlying risk factors, etc. But the example illustrates the larger point. Even small effect sizes can be meaningful, especially when applied on population levels to a large group of people. So the question, how strong is the placebo effect, is hard to answer for several reasons, one of which is that the effect is quite variable. So what influences the power of that placebo effect? The most important factor appears to be the clinical condition in question. Systematic reviews have consistently found that placebo effects are more powerful in managing symptoms and conditions that are largely dependent on patient perception, particularly pain, but placebos are ineffectual in actually altering the course or outcome of disease processes. Other factors that may affect the strength of the placebo effect include the form that the placebo takes and the clinical interactions surrounding the administration of the placebo. There's some evidence to suggest that larger pills may be more effective than smaller ones, capsules are more effective than pills, and injections are more effective than oral medications. Children may also respond to placebos to a greater degree than adults. In addition, the quality of the interaction with a healthcare provider is key. A patient is much more likely to report a clinical effect when they have a positive interaction with a caring, sympathetic physician, rather than just being handed a prescription or a pill. Okay, so what is the placebo effect, though? Let's get back to our cancer patient who reported improved nausea after taking a placebo. So what happened? Well, there are a lot of possibilities, and I've tried to group them into three sort of broad categories, okay? So we'll start with the simplest one. Possibility one is taking the sugar pill resulted in reduced nausea. That is to say, there was actually some improvement in the patient's symptoms. This would be what most people mean when they refer to the placebo effect. This improvement may be objective, so for example, a reduction in the number of times the patient vomited over a certain period of time, or subjective, for example, how nauseous the patient reports feeling. But either way, the improvement is real, and it was caused by taking the placebo. Okay? That's possibility one. Possibility two is that the patient's symptoms did indeed improve, but not as a result of the placebo. Perhaps the patient simply needed to get used to their new cancer medication, after which their nausea waned. Patients do tend to seek care for their symptoms when the symptoms are at their worst. And when they're at their worst, their symptoms are likely to improve a little on their own. This is called regression to the mean. So that is to say the improvement is the result of a statistical effect rather than a medical effect. This regression to the mean is the same phenomenon responsible for the Sports Illustrated curse I mentioned in my segment on liberation therapy back on episode 167. And possibility three is that the patient doesn't truly feel better, but they do report feeling better. Perhaps they don't want to disappoint their doctor, or maybe having a pill to take gives them an increased sense of control over their situation. So, although the pain or the nausea doesn't improve, their overall feeling about their illness does improve.
Mm-hmm. It makes them feel more empowered.
Yeah.
And not perhaps a victim of circumstance.
Exactly. So this set of options, is model number 3, I would group under the umbrella of psychosocial effects, in which if we were doing a clinical trial, we might call this response bias and or observer bias, depending on what specifically we're looking at. For simplicity, I'll refer to possibility 1 as the powerful placebo model, possibility 2 as the statistical model, and possibility 3 as the psychosocial model. And sticklers may note that possibility 2 technically falls outside of the strict definition of the placebo effect I outlined at the top, since it would have happened even if we hadn't given the patient a placebo, whereas the powerful placebo model and the psychosocial model do depend on the administration of the placebo, though the powerful placebo model, we can attribute it to the placebo, and the psychosocial model, it's a bit more complex. So, which of these possibilities is the right one? Well, let's start with Model 1, the powerful placebo hypothesis. For a long time, this was the dominant explanation for the placebo effect. The powerful placebo was in fact the title of Dr. Beecher's influential 1955 JAMA article, in which he stressed, quote, the high order of effectiveness, end quote, of placebos, arguing that it was this power that necessitated proper double-blind experimental protocols. But if placebos do indeed relieve symptoms, how might that work exactly? Well, again, there are a few possible explanations that might be brought to bear to sort of help explain this powerful placebo hypothesis. So we'll call the first one Model 1A, the psychological placebo. Dr. Irving Kirsch proposed that the explanation for the power of placebos is primarily psychological. Not only do patients expect to feel better when they take a medicine, they've also been conditioned by past experience to associate being given a remedy with later feeling relief. So that might explain the power of the placebo. Another option we'll call 1B. In the case of placebo treatments for pain, there may also be involvement of endogenous opioid activation. So endogenous opioids are substances, dopamine for example, that our bodies synthesize as part of our built-in pain control and reward pathways. And these pathways may be activated by taking a placebo. And option 1C is that the placebo, or perhaps simply the patient's belief in the placebo, somehow facilitates the body's own healing processes by some mechanism that is beyond our current understanding. We can call this the mind over matter model. This may be the explanation you were given when you first learned about the placebo effect. It's certainly the story that I was told.
That tracks.
Yeah, if you know my family. This particular mind over matter model is reminiscent of Rhonda Byrne's The Secret and similar spiritual claims, and it is popular among alternative health practitioners who tend to present it as both A, the self-evidently true explanation of how placebos work, and B, therefore evidence of all sorts of baseless claims about the ways that these providers can, in turn, stimulate your body's own natural healing properties with their alternative therapies. This mind over matter hypothesis is the easiest to dismiss on the basis of the evidence. A significant and growing body of research has demonstrated that, by and large, placebos do not alter the course of disease. They don't really heal anything. A large body of evidence now shows that placebo effects simply do not exist outside of symptoms, such as pain, that are heavily dependent on the patient's perception. Between 2001 and 2010, a series of systematic reviews was carried out by Asbjørn Krabjertsen and Peter Gutsche. These papers, published in the New England Journal of Medicine and the Cochrane Library, examined hundreds of studies that compared placebo treatments to no intervention for 60 different clinical conditions. They concluded that placebos do not have important clinical effects, and found that their power was limited to subjective effects, especially pain and nausea. But they caution that even these findings may overstate the placebo effect, as it is still exceedingly difficult to differentiate a reduction in the perception of pain, the psychological model, 1A, from biased reporting, the psychosocial hypothesis, model 3. This research has not been met with universal approval. I read an analysis by Hoek et al. That purported to use a similar meta-analytical method to cheekily show that placebos were just as effective as active interventions. But Krabjertsen and Guttsche's data is much more compelling from where I sit, and the evidence continues to mount. A 2018 meta-analysis of placebo versus no treatment for insomnia supports these findings. The authors conclude that, compared to no intervention, a placebo treatment resulted in patients reporting improved sleep onset latency, i.e., how long it took them to fall asleep. But when their sleep onset latency was actually measured, there was no difference between the placebo group and the no intervention group. So, even for something as sort of wishy-washy as trying to fall asleep, it was in fact Model 3 that was in play for the placebo. The patients perceived an effect, or at least they reported that they perceived an effect, but no such effect actually existed. So whence then the power of the placebo? A careful reanalysis of the studies Beecher examined found, quote, no evidence of any placebo effect in any of the studies cited.
What? A researcher lied? What?
Interesting.
Well, not lied necessarily, but remember how there's this technical distinction to be made between placebo effect and effect that was reported in the placebo group that would also have been reported in a no-intervention group.
Mm-hmm.
So the authors of this reanalysis attribute Beecher's original findings variously to spontaneous improvement, fluctuation of symptoms, regression to the mean, additional treatment, conditional switching of placebo treatment, scaling bias, irrelevant response variables, answers of politeness, experimental subordination, conditioned answers, neurotic or psychotic misjudgment, psychosomatic phenomena, misquotation, etc. So there's a lot of interesting reading that you can do about this reanalysis. But in brief, our statistical and psychological models represent the vast majority of these findings, with a dose or two of scientific malfeasance thrown in. In an editorial for the New England Journal of Medicine that accompanied the publication of Hjorbertson and Guttsche's first meta-analysis, Dr. John C. Bailar III compares the placebo effect to the Wizard of Oz, who was powerful because others thought he was powerful. But when examined closely, he was found to be neither magical nor powerful. quite small and ordinary. We're left with a couple of questions, I guess, several of which listeners might have encountered before. Should doctors be prescribing placebos for their placebo effects if you don't have a good treatment? Or could you argue that alternative medicine is okay because it harnesses the power of the placebo effect? These are both arguments that I've heard made seriously. But the answer to both, I think, should be no, not really. First of all, real medicines equally harness the power of the placebo effect, if such a thing can be said to exist, in addition to their true physiological effects. There is evidence to suggest that a non-trivial component of the perceived pain relief with conventional analgesics is due to the placebo effect. This has been assessed by way of so-called open-hidden studies, in which all participants receive the same painkiller, but some are told that they're getting a painkiller, and some are not told that they're getting a painkiller. These studies have consistently found that painkillers are more effective, much more effective, when patients know that they are taking them. But perhaps, more importantly, there are real dangers in the deliberate use of placebos by physicians. In his editorial, Dr. Basilar wrote, quote, "Few physicians would argue against using innocuous means that might relieve their patient's symptoms or reverse the course of illness. Unfortunately, placebos may not be entirely innocuous. They may divert patients from seeking more effective treatments. They may mark symptoms that need attention. They add to the cost of treatment, and they may have unexpected physiological effects. There may also be some reason for concern that regular reminders of illness in the form of placebos may make a person less rather than more comfortable. The deception that is inherent in the use of placebos troubles some physicians as well as ethicists. This deception may damage the doctor-patient relationship in subtle ways. There's thus reason for caution about the casual acceptance of the notion that placebos can't hurt." As for Hjalbertson and Goethe themselves, they conclude that the use of placebos outside of a clinical setting cannot be justified. We're at the end here. That was a long segment. I'm just going to briefly summarize. At the beginning, I laid out 3 categories of explanation for the placebo effect. Number 1, the powerful placebo model. The placebo's actually doing something. Number 2, the statistical model. The placebo's not doing something, but something does happen, and it is attributed to the placebo, okay? And number 3, the psychosocial model, where somebody reports a benefit that doesn't actually exist. It has long been recognized that all of these factors play a role in the so-called placebo effect. But the current body of research suggests that the power of the placebo is extremely limited, able to address only a small number of subjective concerns, and less effectively than those medicines that already exist to manage them. In fact, the majority of the effects commonly attributed to placebos are not placebo effects at all, but merely biases in reporting and statistical quirks, which, as mentioned previously, technically fall outside of the strict definition of the placebo effect, since they would occur even if there were no intervention at all. Regardless, they are probably the most significant contributor to the situation in which someone takes a placebo and then feels better, which at the end of the day is what matters. Dr. Byler's editorial concludes, "Future studies may show either that placebos have benefits not yet documented, or that the appearance of small benefits, for example for pain relief, is in fact illusory. At present, I would not want to prescribe or receive a placebo without some reason that was far more specific than weak evidence of some general placebo effect."
Good segment,
cool.
Jem.
Thanks.
Any final commentary before we move on?
Glad that you talked about it being some combination of the 3 factors there, and then those other ones that fall outside of the strict definition, because that's very much the case. And I also couldn't help but think an extension of that is how you ask the questions is going to determine how you get the answers for things. So going in and saying, "Is your nausea better today?" is going to elicit a much different response than, "How are you feeling today? What symptoms are you having, if any?" Even going in there saying, "What symptoms are you having?" versus, "How are you today? Tell me about how you are," something like that, is going to elicit different answers from the patient. And not everyone is good at asking very open, broad questions and being able to whittle it out. It is actually much, much more common to ask very specific questions because we want a very We want to get a yes or no clear answer.
Right.
However, is your nausea better today? And again, I'm not saying every researcher is saying this, but I would put good money on a lot of clinicians saying something like that is going to force the patient into something.
And there's utility in both open and closed-ended questions.
Of course there are.
They serve different functions, but we do know push-pulls are a thing, right? We know that the way questions are phrased can have a significant impact on the answers that we receive.
Right. And I'm just thinking of my own experience with things when I talk with people in my counseling, in my previous role, about making changes in some way that they want to make, and talking with them at a follow-up appointment and how they'll report things being different. And then when you get into asking some of the specifics, it sounds as though nothing has changed, but it's very much that outlook part of it. So I think that part is an interesting part because, like you said, with the example of the sleep latency, or the sleep onset latency rather, not much has changed, but they feel better about it in some ways, perhaps. And so I've had a lot of clients, or I've had experiences with clients where they talk about, oh, things are going much better. Yeah, I feel I got more energy, blah, 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 blah. And then when we actually talk about how they're eating, I can't really determine any meaningful difference. But at the end of the day, they feel better about it. They feel more confident about it, and it's making their life better, which is interesting.
They report feeling better, right? And as you mentioned, with the sleep latency question or any of these other questions, if you say, so did the pill that I gave you help? Then it's going to be much harder to say no than if you say, so how are you feeling lately? And they might say, well, I'm still having trouble with this or that.
Yeah.
So you do have to exercise caution there.
Of course. I guess one thing that I think is important to point out, or not point out, but highlight, is that the subjective experience it's really important. Yeah. And I know you know that. Yeah. And I think a lot of people and researchers and that know that. It is not the importance of it to somebody's day-to-day life and experience of their world is not well captured in a lot of the literature. And so things that can help, I'm totally on board. I don't think that you should be prescribing placebo pills or not telling people what you're doing or any of that. And I think that it's important to say, if there are things that can help a person feel better about things, even if it doesn't really change things, that experience of it that makes a difference in their day-to-day life and the quality of their moment-to-moment being.
Absolutely.
That's all I wanted to say with that. It's a side tangent, really, but it's something that's not well captured. Yeah. Or the subjective, it's just lumped into those subjective experiences. But think about your day and how much of your day is colored by the subjective experiences that you have on any random day.
Absolutely.
A real big part.
Yeah.
A real big part, right? And so you can have effectively the same day at work, but or like the same routine from the time you wake up to the time you go to bed. And the whole day can be so different based on your subjective experiences.
Absolutely.
Even if like you ate exactly the same and you had all the same routines, right? So it's one of those things that again, I'm on a side tangent, but it's something that it's really hard to quantify, and I get that why we don't do that, but it's really important.
And that's one of the reasons that it's so important to harness these things that we talk about to exaggerate the placebo effect. Like, one of the most important factors is that provider-patient relationship and the way the clinical encounter happens. That is one of the biggest influences on the strength of the placebo effect, and that's going to affect, regardless of whether it's a placebo or not, it's going to affect that patient care to a significant degree. And unfortunately, we're in the situation where for every subjective condition that can be treated with a placebo, as far as I can tell, we have more effective active treatments available for them, right? So it's not to dismiss patients' experience of pain, but we do know that placebo will be roughly 1/3 as effective, according to the research, as an NSAID for pain management. So, yeah, you could say the placebo has an effect on this subjective thing, but the NSAID has that placebo effect times 3, depending on the kind of pain. NSAIDs are less effective for certain types of pain, but
I'd much rather have that than no placebo for me. Thank you.
Anyway, maybe this is something that we'll revisit, and I would be interested to hear from our listeners if they have any thoughts on the matter.
Well, thank you.
Sucker love is heaven sent you. Pucker up our passion spent. My heart's its art, your body's rent. My body's broken, yours is bent.
Well, this came to me because Ashlyn, Dave, and I are currently in the midst of a bathroom renovation. We're doing most of it ourselves, not by choice, but we did have a professional come to install the new toilet in our main bathroom because, well, mostly we got a fancy one with a bidet, a remote control, and the most exciting part for me, straight sides, so you don't have to clean in all the little crevices.
Oh, I hate toilet crevices. They're the worst.
So, looking at this toilet got me thinking, knowing that this extraordinary science of everyday things topic was coming up. So, the inner workings of a normal modern toilet are simple enough that even I, with my negative plumbing knowledge, can usually see what's wrong. But the how and the why of the workings intrigued me.
Mm-hmm.
Surprise, it's actually some pretty fancy physics. Well, fancy.
It's really cool.
Like me. Yeah. To really understand how a toilet works, we need to look at Bernoulli's principle of fluid dynamics. But before we get into the principle and its related equations, we should back up just a little bit. No pun intended. So after all, Daniel Bernoulli published his theorem in 1738, and some forms of water-assisted toilet have been around for much longer than that, including back to both the ancient Indus and ancient Greece civilizations. A basic gravity toilet uses, well, gravity to flush waste. When you press down on the flush handle, the valve chain opens the flush valve, which causes all of the water in the cistern, which is the tank part of the toilet, to rush into the bowl. This water is then siphoned out through a tube connected to the sewer or storage tank, and it takes away the waste with it. The water running out of the cistern and into the bowl drops the big rubber floaty thing in the cistern, which opens the inlet valve and lets more water into the tank. Once that float ball is floating level again, it closes the inlet valve and it's ready to flush. That usually takes about 8 seconds. So where the Bernoulli principle comes in is during the siphoning stage. Here we are getting into fluid dynamics that make my head spin, so I'll be quoting liberally from Lee Knight's article on the MIT website. The Bernoulli principle can be derived from both the principle of conservation of energy and also of Newton's second law of motion. If a small volume of fluid is flowing horizontally from a region of high pressure to a region of low pressure, then there is more pressure behind than in front, right? Make sense? This gives a net force on the volume, accelerating it along the streamline. So the equation that we use for toilet flushing is pressure at outlet divided by density of fluid plus velocity of fluid out squared divided by 2 plus gravity times the height of the outlet.
I know some of these words.
It looks much better when you have it written out, but we can't really do that in a podcast.
I am
This
so
is just
confused.
word salad.
It's so many syllables going on here.
I'm getting flashbacks to when I was studying for the MCAT via audiobook.
Oh,
Yeah.
God.
So just trust me, it's a very long-looking equation. says-
Yes.
That talks about the pressure at the inlet versus the pressure at the outlet, and they have to equal out using all of these different items, basically. If we know the time that it takes for the toilet flush to cycle, so approximately 8 seconds, we can determine a rough estimate for the flow rate. Using that estimate and the approximate area of the pipe, so the size of the pipes, we can estimate the average velocities that we'll need both from coming from the cistern to go out the pipe. And since the flow rate is constant through the system, according to the law of conservation of mass, and assuming that the density remains constant, we can figure out the required water and time for the velocity in order to make the siphon work. All that said, it comes out to about 7 liters with each flush. I'm not a physicist, but even I can see that that is some pretty extraordinary science to remove your poop with each flush. And I can never look at the toilet the same way again. Now, a gravity toilet is only one style of toilet out there. It is the most common still. You also have vacuum toilets that use less water. You'll mostly see these in vehicles that can't have a giant cistern of water to flush, so like an airplane or a bus, or on a rocket ship. There are also pressure assist toilets, which include a large air bladder to propel a smaller amount of water through the pipes. However, sometimes older pipes cannot handle this large rush of air, and it will blow out the back of the toilet. It will destroy your pipes if they're not upgraded for a pressure assist. There are also, and this is gross, they're called macerating or upflush toilets. And these are convenient for places where you cannot or do not want to route new pipes. So they use a pump, which is electrically powered, to force the waste through a chopping blade to get it to go through a smaller outflow pipe. And finally, there are composting toilets that allow us to turn human waste into safe compost for gardens. These require a very large storage tank, and you're not going to find them in most houses. And through all this, after all these thousands of years, the basic gravity toilet, using Bernoulli's principle for siphonation, is still the most popular for our areas of the world with access to municipal plumbing. And that's how to look at your toilet a little bit differently.
So with low flow toilets, that some of them use less than 7 liters, I believe.
Yeah.
Are they using a pump or one of the pressure assisted things?
I think there's some pressure assist going on, but you can get them in non-electrical versions as well, so I'm not sure what magic is working there. If they're just changing the inflow and outflow pipe sizes, like the height sizes, and then that would, if you change that, that changes the pressure using the equation if you punch in different numbers. So it might just be using more forceful pushing of water.
Right. Okay. That's really interesting. That's, yeah.
And it's amazing to think that, like, it's a toilet. How does a toilet work? How does it get the stuff out?
Like, it makes sense, but it's also just like, wait, well, but how?
Yeah.
Right?
Tell me the science.
And like the question of, I always had this question when the power would go out when I was a kid. It's like, can you still flush the toilet? Like, well, if your water's running.
Yeah. If you're connected to
I was always told yes, but once.
Yes, that's what I was told as well, because you'll be able to flush with whatever's in the tank, in the cistern, but then it may not refill properly.
Yeah.
Depends on how you're getting your water.
Exactly.
Yeah. I grew up in an area that it was electrical pump water. So yes, you could only flush once.
Yeah, see, I grew up in a house with our own well.
Yeah, same.
Yeah, so did I.
Well.
Yeah.
Bunch of country kids.
Bunch of country kids. Yep. Cool.
So that's toilets.
Okay, up next we have Laura, who I don't remember if she ever told me what her topic was.
I didn't.
Okay.
I'm going to open my segment with a question for you all. What do bread, soap, and my mattress all have in common?
I know the answer.
Jem knows the answer.
In the in the United States, they will all be deregulated very shortly due to a...
Wow, dark.
Okay. Let's keep this light here. I'm talking about foam. Foam is amazing.
Woo, foam.
So, yes, these are all examples of foams. I wasn't sure if I would get you with the bread, but Ashlyn, the baker here, definitely got that one, which I'm glad. And I want to talk about foam because it is ubiquitous. It is in our food. It's part of our housing and construction. It's used in chemical processing. It's even used in acoustics. It's used for many, many different things. And foam, at its core, it's not that complicated. Really what foam is it's a gas, usually air, but it can be other gases as well, that's dispersed in a liquid. And it's done so in a way, there are many, many, many little bubbles or air pockets that are made, and it changes the structure of that liquid. So it is no longer gas and liquid. It is something actually more solid-like, even though that it doesn't necessarily have the strength of many solids like we would think of, but it's more, it's different. It acts different than either the gas or the liquid parts of it.
I'm sure it's not technically a colloid for a bunch of reasons, but like the concept, thinking about it, reminds me of a colloidal suspension.
Colloidal suspensions do come up a lot when you read the research around it, but it's not a colloid. Yeah. Like it does talk about some similarities to it, but it's not that. And I believe part of that has to do more so with the size of the pockets in it, and then the structure and the way that they interact with each other.
Yeah.
Okay, I have a question.
Yes.
Is today going to be the day that I learn what the difference is between closed cell and open cell foam?
I can tell you.
So maybe.
Because I also learned the difference between it.
Excellent.
So foams come in many different forms, as we can all think of things that are foamy, I'm sure.
Many different foams, Laura.
That's just a phoneme, Jim. Speaking of phonemes.
You guys don't get real names anymore.
Nobody gets names.
I'm Laura Creek Bailey with my husband, Jim Newsman.
Jim.
Oh, I'm sorry.
Oof. Oh, God. All right.
Foam. Many different foams.
Many different foams. Yes, there are many different foams. And like the examples that I gave in my opening question, not all foams are the same or even similar if you really think about it. Their structure is there, but what they are is very, very different. So very briefly, to answer your question, Ashlyn, closed cell foams are foams where all of the bubbles are separate. The bubbles do not interconnect. Open cell foams are where the pockets connect to one another. So a kitchen sponge is a classic example, especially the cellulose type, like the type that we use at home here, that has the very irregular bubbles. That is an open cell foam. It allows, and the open cell of it is what allows it to absorb water really, really well. A closed cell foam would be something like your neoprene wetsuit, something like that, where it's, or that type of a material there, where you actually, the bubbles are there, but they do not interact with one another. They do not connect.
Fucking bubbles!
Actually, a really interesting example here is bread as a foam. So if you want to go with the idea of bread as a foam, when you are first rising your bread, so the gas in the bread is produced by the yeast, it's not injected. Well, sometimes it is, depending on your processing. But let's just go with regular bread. And the gas is made by the yeast. Bread will start off as a closed cell foam, where all the bubbles grow independently. But if you let it overproof, it starts to become an open cell foam. And that's part of what causes the structure collapse.
Oh,
because the bubbles start to interact with one another.
So you gotta let ciabatta get right to the edge.
Yeah. Does that help with your question?
Yes. I guess that I always thought that they all must interact. Like even in the smallest foams, they must touch each other sometimes. But the way you said about yeast, how they start as closed cell and like become open cell, makes me able to visualize that better.
So when I say interact, it doesn't mean that the bubbles aren't touching. And actually, that's an integral part of the foam structure. So if you look at foam under a microscope, you'll see that it has sort of a honeycomb-like look to it, or some will describe it more as a soccer ball look, tetradecahedron type of look there. So it will have many short, flat sides that touch each other. That's important. When it comes to the cells, whether it's open or closed cell, from my understanding, I am not a foam expert, by the way, but from my understanding, it's whether or not the cells start to connect to one another and become tunnels throughout the material. Does that make sense?
So not just that they're side by side, but that they actually,
because
like, the walls break down.
The walls break down, but form a connection. It's not because
it's not just that the bubbles merge. It's that they stay kind of separate but are connected, right?
Yeah, there's different components of that. Again, I'm not a foam expert. We've basically reached the limit of my knowledge of closed and open cell foams, but that's what I've learned so far.
Thank you for the explanation.
Yes. So in a foam, like I was saying, foam is basically made of a whole bunch of bubbles that are surrounded by a thin layer of liquid, a liquid film that makes the wall of these bubbles here. As I mentioned, all foams start off as gas in liquid. So we talked about the bread. Bread isn't liquid per se, but if you call it a semi-solid paste, then you get more into the liquid there. But we all have examples of those solid foams, right? Think of styrofoam or spray foam for anybody who's done any renovation or fixer-upper work. So these are solid materials, but they're still foams because they have the multiple air bubbles. And they all started off as liquids. It's just some foams are made of things that will then harden. Or in the case of bread, it hardens because you bake it, and that solidifies the structure of the proteins and the starches. So that's what a foam is. So foams come in a variety of structures. They're not all the same, and if you've ever looked at different types of foams, you can tell. Some of them have very regular types of bubbles. Some have very varied types of bubble sizes or shapes. Some are very light. Some are more dense. Some will have large bubbles. Some will have small bubbles. So foams come in many, many different ways. And this is part of what made foam interesting for something to talk about, because it is so variable. And it's actually something that there are researchers and people in industry and those who work with foams in different ways still haven't found exactly the precise ways to make foams work the way that they want them to. It's only in the last couple of years even that certain aspects of foam structure and destruction have even been elicited through research. So as much as foams have been around for a long time and we've been using them, actually making a foam work the way that you want it to with the substances that you want is quite complicated. And there are many forces at play when it comes to stabilizing foams. So you have the force of gravity, which is a really, really big one, of course. You have surface tension, you have inertia, you have the viscous stress, you have the chemical properties of the substrates that you're using as well. And then you have the interactions between all of these. So I'm going to put a long paper about the physics of foam that I read and partially understood into the show notes, but it has a good little diagram of how all of these different forces interact with one another. And you can see that it really becomes quite complicated. So it's not that foam itself, the concept is difficult. It's that if you want to make a foam that has properties X, Y, and Z, it's actually really tough. And in some cases, we haven't figured out how to do that consistently yet, which is kind of interesting considering the number of foams that are out there. One of the big things that makes foam work too is the addition of surfactants. So this is some kind of additional chemical or substance that increases the surface. Additional magic, yes. That increases the surface tension of the bubbles. So if you think of a foam made of pure water and air, it basically doesn't exist because the surface tension won't allow for that. So if you want to then have a bubble bath, you add bubble bath solution, which has a whole bunch of surfactants in it. And these are things that allow that water to build stronger walls around those air bubbles. But you'll also notice that that type of foam that you might have from your bubble bath is different than what you might have from a shaving gel foam. Even if you look at those two foams, the bubble size is quite different, and just the feel of it, the texture of it is really different as well. In order to do that, you have to use different types of surfactants. These can be all sorts of things. They can be chemical substrates like sodium lauryl sulfate is really common when it comes to cosmetics. When it comes to foods, proteins or fats will be those surfactants as well. So there's a lot of different things that you can do with it. And as people try to develop foams, you have to understand what the intended purpose is too, because again, that's another factor that's going to go into it. So if you want your foam to last a really long time, you need to have a surfactant that's going to last. You need to know that how to create a bubble size that's going to work well with your surfactant, because how you inject the gas into the liquid will determine how regularly or irregularly the bubbles are arranged, which will then affect the structure of the foam. It will also affect how uniform in size the bubbles are. So your product is either going to have the desired effect or it's going to fall flat. If you're looking at something that needs to harden, like in the case of spray foam, you need the bubbles to expand well enough, but to get the size that you want for the structure that you need. But then the product also needs to harden fast enough to hold on to that bubble. And so, again, there's all these different forces. I'm not going to start listing out formula the way that Lauren did, partially because I didn't put in my notes and partially because I will confuse myself.
I confused me, and I'm still confused. So good choice.
Onto that note of particle size, too, the gas that you use can make a difference. And I actually want to use beer as a good example of this.
Beer is liquid bread. It's good for you.
So as we know, most beers get a bit of a foam on them when they're poured from draft. However, the type of gas you use is going to affect that type of foam and how long it lasts. So your standard kind of American lager, it's going to have a tall foam, but it's going to get flat pretty quickly. They're using CO2 or carbon dioxide in that. Whereas if you look at Guinness, which is I'm looking at Jem over here.
Your nitrogen.
Yeah. And so not being a Guinness drinker, I had never thought of that before. So this was news to me, but I'm sure all the Guinness drinkers out there are like, well, yeah, of course. But Guinness uses nitrogen, which produces much smaller bubbles, but allows those bubbles to stay in the foam a lot longer.
And actually, a lot of cold brew coffees also use nitrogen.
Yes. And again, so in a cold brew coffee, you're going to have fewer surfactants and things like that. I mean, coffee will still does naturally have some options for that. They will have some proteins that will allow for some foaming, but you'll want to optimize that. And so nitrogen will do that for you. And I also learned that the ball in the bottom of the can is filled with nitrogen.
Yep.
And so when you open up the can, it pressure releases nitrogen and allows the bubbles. Again, not a Guinness drinker. I'm sure many of you are just like, yes, we know. But it was interesting to me. So.
I didn't know the little ball had nitrogen in it. I thought the little ball was just to make it into like a cat toy.
I thought it was to deal with sediment or something like that. I had no idea. I just didn't look it up because I don't drink Guinness. So it was just one of those things. But yeah, now you know, Lauren. Now you know. All right.
Still just going to be a cat toy for me, so.
So I want to talk about foam in food for a minute, and specifically in beverages. When it comes to beverages, having foam on top is going to be a good thing for you because it means you're going to slosh less of your drink if you're walking around with it. The foam is going to absorb a lot of the shock from you taking steps or you moving your arm. And so you're going to spill a lot less coffee. So if you're someone like me who hates having coffee splash up through the opening in your travel mug, get a cappuccino with some foam on it.
That's really interesting. That had never occurred to me that had that utilitarian purpose.
It really does.
I did not know that.
And that is actually something that's extrapolated to a much larger scale. This is really important in industry because if you think of sloshing around in your coffee cup and how annoying that is, imagine a tanker truck full of like combustible liquid sloshing around in there, building up pressure.
Yeah.
That's not good.
Consequences for hydraulics.
Exactly. So using foams as anti-slosh in those types of liquid transportation is a really, really helpful thing to help keep everybody safe and to help keep the integrity of the product. Also, on coffee, interesting that at least when it comes to instant coffees, there is some research showing that coffees that have more foam on top of them, and we're not talking about the foam from a latte per se, because that's a different type of foam. That's mainly the milk being foamed from the proteins and that. I'm talking about coffee itself, black brewed coffee. When it has more foam on it, it actually seems to have more aromatic compounds. The foam seems to hold those in. So a foamy cup of coffee is likely to be more flavorful than a not foamy cup of coffee.
Very interesting. Is it like the smell molecules or the flavor molecules distributing over a larger surface with the foam?
Well, I'm not entirely sure. I'd have to read into it again, but my guess is that like the things that are the smell molecules, those are the aromatics and they're volatile, which means that they turn into gases really easily. So there seemed to be a connection between having more of those volatile compounds, but in the coffee and more foam versus if you didn't have as much foam, you wouldn't have as many of those volatile compounds. So I'm not sure if the foam is keeping them in or
it makes sense that as they try to escape the surface of the coffee, they get like trapped in the foam.
Because the foam would slow that. And that's when you think of foam as a fire retardant. That's a really important thing that it does as well. It slows things down. So foam can have lots of really important applications in things like safety. Also in cleaning, right? If you're cleaning particularly a surface that needs long contact with the cleaning agent or a vertical surface, you actually do want a foam compared to a liquid because the foam is going to slow down the transit time and give more contact time with the cleaning agent. So
those are the so-called scrubbing bubbles.
exactly, the scrubbing bubbles. So it's not that the bubbles themselves scrub or the effervescence scrubs or anything in this case. It's just that the foam allows it to cling and actually do what it's supposed to do. So we've all probably heard that they add the bubbles to things like hand soap and toothpaste just to make it feel like you're cleaning. And they do, in fact, do that. So some foams are not useful. But in certain cases, some cleaning foams are actually useful. On the flip side, for things like dish detergent, you actually don't want it too foamy because it's too hard to rinse off. It's too hard to get rid of the bubbles.
Interesting.
So we use foams every day, whether they're manufactured or even just part of our foodstuffs and the natural world. There are foams all over the place. They play a lot of really important roles. Scientists are still figuring out how to make foams work the way they want them to, and they're always finding new ways to use foams and interact with them. Foam!
That's really cool. Like, I've literally never thought about the different types of foam, so thank you.
Right.
Laura. That was awesome.
Well, awesome. I'm glad that I gave you all something to think about. Bread is a foam.
Foam no longer sounds like a word, though.
It doesn't. No.
It's a structure.
All right. That is all.
Awesome. So that is all of our small everyday sciences, and they were all wonderful. That was a lovely show.
Mm-hmm.
So maybe that's my something nice. I don't know. I'll think about it. What's everyone else's something nice?
Sure, you're going to have to pick somebody in specific.
Yeah,
All right, I'll go first.
Teacher call on
Accuse
someone.
Yeah.
Yes. I will go
Lauren,
first.
j'accuse.
The reason Ashlyn and I both sound a little drunk tonight for this recording is we spent the day in the truck driving home. We had a visit in Thunder Bay with my family. We haven't seen them since before COVID hit. So it was a nice and it's never a relaxing visit because there's always so much to do and so many people to see. But we had quite a few days of chilling with my family and it was nice to see them.
That's
my
really
something
nice.
I saw my
I like that.
We had a lovely time with lovely food, and there were a bazillion chipmunks and squirrels to laugh at every day. It was pretty great. Except for the mosquitoes. The mosquitoes were not great. But that wasn't their fault. Laura, what's your something nice?
My something nice is going to be my garden. I don't think I've talked about it yet this year, but it's coming along. My lettuce is producing a literal ton of lettuce. It is a lot of lettuce, and I'm quite enjoying having fresh lettuce all the time from my garden, and just seeing it start to grow and bloom, and seeing some of the little fruits starting to form, and I like that.
Awesome.
So I've been giving lettuce away to anybody that will take it.
My something nice is video games again. I have had a bit more time for reading lately, and I've been reading The Left Hand of Darkness, and it's good, but everybody knows The Left Hand of Darkness is good. I mean, it's been around more than 50 years. If you haven't read it by now, give it a read. It's aged mostly pretty well, I think. I don't know. Ursula K. Le Guin is great. But my something nice is video games. I have had some time since finishing school to play some video games, and I particularly enjoyed Citizen Sleeper, which is available on PC or Nintendo Switch. It is a kind of mechanically, like there's a sort of a dice game component to it. It's kind of has almost a bit of a board gamey feel, but it's a single player narrative game about a person, an artificial person, who is sort of trapped on a space station. And the game ultimately it's about a lot of things. It's about disability. It is also about community and how hard it can be to make your way in the world.
Making your way in the world today takes everything you've got.
But how important it is to make those meaningful connections with other people.
Sometimes you wanna go where everybody knows your name.
It is gorgeous. It's like a sci-fi setting, but it's beautiful and hopeful, very well written. The previous game by that developer is called In Other Waters. I haven't completed that one, but I did play it, and it's also very cool. But yeah, I definitely recommend Citizen Sleeper for a single-player game. And bonus multiplayer game, if you want to just have fun with some friends, play Teenage Mutant Ninja Turtles Shredder's Revenge. I've been playing that with some friends. If you are a young Gen Xer / elder millennial like Lauren and I are, who liked frequenting arcades, then this will be familiar territory. It is a Ninja Turtles beat-em-up game, except it plays so much better. It plays the way you remember those games playing instead of the way they actually played, which was not actually that well, those Konami games. But if you liked the Ninja Turtles arcade game or the Simpsons arcade game or the X-Men arcade game, it's that kind of thing. Really solid, really polished, and the netcode is really good. Seamless play on Nintendo Switch or on PC with just friends, drop in, drop out. It's great.
But would my button mashing work?
You know what? It wouldn't be half bad.
Okay.
The combat is surprisingly deep. My only real criticism, I think, is that every time you start playing, it's like, here's this 20-step tutorial on how to work all the buttons, but Lauren, button mashing will get you a long way.
Excellent, because that's all I know how to do.
Yeah, so for a single-player narrative experience, try Citizen Sleeper. For a multiplayer, just fun time, try Teenage Mutant Ninja Turtles Shredder's Revenge. Both available on PC or Nintendo Switch.
Awesome. Ashlyn?
I want to say that I really enjoyed reorganizing our trailer. We take a ridiculous amount of things camping. We have 3 huge canvas tents with all of the associated poles, and also poles and a giant metal tray for raised cooking fire, and 18 plywood boxes that each hold a Rubbermaid tote that we use as our bed, and 4 mattresses, and lots of bins. I don't know, am I missing any significant items? Armor, weapons. And I'm, with Dave and Glenn, my father-in-law's help, we managed to figure out a layout that makes it so that we can get any tent out without moving anything else, and we can get to every item in there without having to move anything out of the way. I'm so proud.
Nice.
Wow.
That is awesome.
So if I just want to put up a day shade, I don't have to rummage around a pile of 600 pounds of wood to find the 4 poles that I need. They're in a slot on their own. I can get them. I'm so happy.
Nice.
That is a something nice for sure.
And we still have tons of room for when we need to throw stuff in there. So if listeners have any good hobbies that involve camping, but not children, not children focused, there can be children there, but I don't have children, I would like to know about them. I need a new camping hobby because we have all this camping stuff and it's really well organized now. That's my something nice. So what are we talking about next month, Jem?
So next month, we are going to be talking about fake astronomy.
What?
Astronomical pseudosciences.
Ah, specific.
Oh my.
Yeah, we're talking about pseudoscience in space. Pseudoscience in space!
That sounds fun. All right.
Thank
you very much.
Night.
That was a lovely show.
Mm-hmm.
It was.
Good night, everyone.
Thank you, everyone.
Thank you.
Show notes and references for all of our episodes are available at lueepodcast.com, where you can also find links to donate or get in touch. If you'd like to support the show, the best way to do that is with a review on Apple Podcasts, or wherever else you found us, or by sharing this episode with a friend.
Life. Don't talk to me about life.
You're listening to Life, the Universe, and Everything Else. Today on the show, the chemistry of colored glass. Nope, that's the title of my segment. Today on the show... it's been a really long day. We're talking about the everyday awesomeness of shit.
You're gonna try that a third time?
Yeah. Oh, please make me sound less tired than this, Marissa. Thank you very much. My name is Ashlyn Noble, and I'll be your host tonight. With me today, I have Jem Newman.
Hello.
Laura Creek Bailey. No.
Whoa.
Jesus
Nope.
Christ.
Did I marry you,
No,
Lauren?
try
I
again.
don't remember that.
Oh my god. Why am I doing this?
That was pretty good.
Oh, boy.
Today on the show... No, we already did that. My name is Ashlyn. I have my segment pre-written at least. I don't have a script for this part.
You don't have a script for saying your spouse and friend's name?
Correct. That is the part I need a script for at this point. Whew.